Assalamualaikum everyone, welcome back to CSE 423 projection. And in previous lecture, we discussed about a simple purpose perspective projection where the center of projection was on the z-axis. But what if it's not on the z-axis? If it had some arbitrary point like 20, 30, 40. So what does that indicate? So it indicates that it's not on the z-axis. In order to be in the z-axis, it should be have an x and y value equals to 0, and it can have an arbitrary z value. But what if their x and y value is non-zero? What's that if that's the case? So our projection diagram looks like similar to this. It's similar to a perspective projection, but with one difference, with that the COP is not necessarily on the z-axis, but it could be on the z-axis, but it don't necessarily it's necessary to be on the z-axis. So the 2D diagram for it is like this. So as you can see here, our rest on the right is fairly similar to a previous one, but on the COP, if you look at here, previously it was on the z-axis, which is the baseline. It's now in up here. Could be also down here. Also could be on the z-axis itself. And in this case, we don't necessarily need to care if the COP is at origin or projection plate is at origin. We don't need to know this. We may need to know the distance between the COP and projection plane, because we need this value to calculate the COP itself or the projection plane's Z value. But if it's not given, now COP is a 3D point. We can write it component wise at COPx, COPy, and COPz. And this baseline is the z-axis. It's shown here. It essentially pierces through the projection plane. So our projection plane is this line. So it's from the shown from the side. So our projection plane is this one. The projection plane also extends to the lower part, but it's not shown here. Only relevant parts are shown. When it intersects the projection plane, it intersects through a point called 00ZP. So since this is the z-axis, on the z-axis, every x and y value are 0, but it has a arbitrary z value. So we'll call it ZP. So the difference between COPZ and ZP will be our distance. So our distance was the distance between COP and projection plane. To calculate the distance or calculate the COPZ or the ZP, we'll need the distance value, whatever it's given. If we given any two of these values, we can calculate the third one. All right. In order to derive the formulas for general purpose perspective projection, we need to do some setup. So what could be these setups? So we imagine a vector. So this vector runs from starting from 00ZP, which is our intersection point between our z-axis and the projection plane. So 00ZP, and it goes towards our center of projection. So it goes from 00ZP and COP. So this direction is indicated by this Q. So we are deriving this vector from 2 points. We need to subtract these 2 points to get the vector. So in order to calculate Q, we need to subtract 0ZP from our COP. So it will give us this expression. So COPx, COPy, and our Z component will be COPz minus ZP. And this vector is called Q, in which is component wise it is expressed as Qx, Qy, and Qz. It's also sometimes written as QDX and QDY and QDZ. So D stands for difference. So since we are calculating the difference from these 2 points, so it's sometimes expressed as like this, but we will maintain this expression Qx, Qy, and Qz for brevity, and since it will make our expression look even smaller. Now we will separate these 3 components into 3 separate parts, or 3 separate equations to be precise. So Qx equals to COPx, Qy equals to COPy, Qz equals to COPz, and we can arrange them into this formation. We are treating the left hand side and the right hand side. We'll mark each of these equations as equation 1. So equation 1a, 1b, 1c. Now we'll notice one thing, which is our projection ray, or so-called projectors. So our projection rays start from our target point, which is P, and goes towards our center of projection, which there are infinite number of projection rays, but all converges into our COP. Here only one is shown because we need to, for derivation, we only need one. So we imagine it as a line segment. So the line segment starts at P and goes towards COP. We can also consider it like it starts at COP and goes toward P. Both are correct. And for this line segment, we can express it as a linear equation. More specifically, our parametric line equation, which we saw in our scientific lectures. The parametric line equation will kind of look like this. Pt equals to P0 plus T into P1 minus P0. So P1 is our starting point, P1 can be our ending point. Every point between these 2 points on that line segment specifically can be expressed by Pt for a certain value of t, which is between 0 and 1. We can, for this scenario, we can consider COP to be our P0 and P, which is our target point, to be P1. So COP is here, P is here, and this blue line is our line segment. And you can, as we know, this is our projection ray. This projection ray must pierce through our projection plane. It must intersect our projection plane. And the intersection point is our P prime. So P prime is indicated by this orange dot. And since it's in our line segment, at certain value of t, pt will be our P prime. So at certain value of t, so it could be like 0.8, 0.7. We don't know that. We don't need to know that. At some point, it will be equals, the pt will be equals to P prime. So we consider that specific value of t as tp. Tp is when our parametric line gives the projection point, or P prime. So for the certain value tp, we can write P prime equals to pt, and our expression like COP plus t plus tp multiplied by P1 minus COP. This is the point representation of this equation, but we need to divide them into 3 separate components: x, y, and z, x, y, z components. Here we have done exactly that. We have separated our x, y, z components from our previous equations, COP plus tp into P1 minus COP, and we have got these 3 combinations. So x prime, which we are getting from P prime, and y prime and z prime also. So x prime looks like this, and y prime is similar to this. And where we are getting this qx and qx? It was from our previous equation 1. So COPx equals to was qx, COPy equals to qy, COPz was equals to zp plus q. So COPz was a bit different, but as COPx and COPy was like similar. So if we put this equation 1 values here, we will get these 3 combinations. Now we've got 3 equations. We can equations for x prime, y prime, and z prime. We can calculate these 3 values, but notice here there's a tp term. We don't know what is the value of tp. So we need to remove this tp from these 3 equations, but it's not that easy. First, we need to do some steps where we isolate tp here in the left hand side and keep everything else on the right hand side. We do this from our third equation here, 3c, which is the equation for z prime. So in this equation of tp, we can calculate the value of tp by knowing the value of qz and zp and z, but we don't know the value of z prime. In fact, we need to calculate the z prime. It was our original goal to calculate the value of x prime, y prime, and z prime. So how can this work? Before we go further, let's look into this thing. So this was our projection plane, this perpendicular line. Every point on this plane had an same z value. So 0, 0, zp had the same value as x prime, y prime, and z prime. So we can say zp equals to z prime. So exactly this we have done here. Z prime equals to z prime, since it is on the same plane. This P prime point and 0, 0, zp is on the same plane. So they both have the same z value. So since we know z prime equals to zp, we can make it our own equation 4 and substitute z prime with zp. So we place zp in place of zp, which will cancel out zp and zp, which will give this expression here. We can further transform this expression by bringing this minus qz term into the denominator. So we'll get what we have here is tp equals to 1 by this whole big thing. One thing you may notice that we no longer have z prime here. So this was our equation for tp, which is 1 divided by this big whole term. I'm not going to pronounce that. And another thing we got is z prime equals to zp, which means if we know the value of zp, we can already know this z prime value. So our initial target is to calculate these 3 values. So we can, if we know zp, we already know z prime. So all we left is to calculate the value of x prime and y prime. So we have got this equation tp, which is 1 divided by this big term. We can now substitute value of tp into the equations for x prime and y prime. So we replace this tp with this big value. So we do this only for x prime and y prime. So in the x prime equations, we replace tp with this big term. So we have done qx plus this big term into x minus qx. We do some algebra here. So we do x prime and this whole sort of stuff, and this qx and qx will be cancelled out, and we'll end up with this big thing. We do the same thing for y prime. So in case of y prime, the expression will look similar, and but in places of x, it will just be y. One thing you may notice that both of the equations for x prime and y prime have this same denominator, which was initially in our TP equation. So the TP equation had this denominator, and our x prime and y prime equations have this same denominator. So we can save this denominator with a certain value of w, which we'll do next. So before we do that, let's focus again into our z prime equation. So from previously, we know that z prime equals to zp. So why we are placing a common denominator? We were placing a common denominator to simplify our process of matrix building. But in case of z prime, there is no common denominator unlike x prime and y prime. So we need to forcefully bring this denominator here in this equation. So how can we do that? So one way we can do that is multiply zp with the term called denominator by denominator. What we're doing is multiplying z prime with this big term divided by this big term, which was our denominator, and these two will cancel out, but we will not cancel them out because we are already bringing them here. We'll only keep the lower bottom term here and multiply zp with this upper term, right? So it will look something like this. So this is our equation 5. So this three will consider equation 5. So we have got equations for x prime, y prime, and z prime, and all these three equations have our same denominator. So on the left, you can see these three equations arranged in one place, and as I said, the common denominator here, you can replace this common denominator with w, as we did with our simple purpose perspective matrix. We always replaced our common denominator with w. So which we have done here, and also w becomes its own equation here. The next step we did was move w to the left hand side, so which will make x prime into w, y prime into w, and z prime into w. We don't need to do this for w because it doesn't have any denominator to begin with. So so we have done this here. So we move w to the left hand side. We got 4 equations. Now we can build our matrix. I've rewrote these equations on the right, but with color-coded coefficients. So for all the x terms, the coefficients are red. For y terms, it is green. For the z terms, it's blue. And for the leftover terms, it is purple. We now use the same strategy from before to build our matrix. So we have our 4 equations in this structure, where the right-hand side expressions are like x plus by plus cz plus d. So we collect only the coefficients and house them into our matrix and multiply that matrix with x, y, z, and 1, which is our homogeneous coordinate representation of our 3D point. Using this strategy and our equations from before, so these 4 equations we got, we can now build our matrix. And if we put these coefficients in the matrix, we will end up with this big one. I know it looks kind of scary, but it's actually a very powerful matrix because it enables you to calculate perspective projection for arbitrary COP. So all we need to know is the position of our COP, which is COP x, COP y, and COP z. And we also need to know the z level of our projection plane. So our z level of our projection plane is zp. From these values, we can get these 4 values. So qx, qy, qz, and zp itself. All we need to know is these 4 values. So if we already know these 4 values, we can build this matrix. And if we build this matrix, we can perform our matrix multiplication to calculate our ultimate projection. Now we will look at an example. So this example says our COP position is 10, 90, and 0. So look at this. It doesn't have any non-zero xy values. Its x value is 10, y value is 90. And our target point is 30, 50, minus 200. And our projection plane is 200 units away from our center of projection. Now notice that the center of projection has a z value of 0, and our target point has a z value of minus 250. To our best knowledge, the projection plane, which is this one, must appear between these 2 points. So the z value of our projection plane must be between 0 and minus 250. And anything between these two z values, which is 0 and minus 250, must have a z value which is negative. We already know the distance between the projection plane and COP, which is 200 units. So we can just subtract 200 from our COP Z value to get the Z value of projection plane, which is minus 200, which is essentially the ZP value. So we already got to know the ZP value. So we now need to calculate the QX, QY, and QZ. So these three QX, QY, and QZ value actually constitutes the Q vector. So how can we calculate that? Notice our formula for calculating Q was COP minus 00ZP. So we already know this coordinate of COP, which is 190 and 0. And we already know ZP from our previous slide, which is minus 200. We can apply this formula to actually calculate our vector, which is Q vector, which is 100, 90, and 200. So Qx is 100, Qy is 90, Qz is 200, and Zp is already minus 200. So we already know this 4 values needed to build our matrix, right? So we can now apply these 4 values to build our matrix, which is, if we put these 4 values here and into our matrix formula, we will end up with this matrix. We have already got our matrix, and our target point was 30, 50, and minus 200. We need to mount this target point into a column vector. So we have mounted this point into a column vector, which is 30, 50, minus 250, and 1. Since this is a homogeneous coordinate system, we multiplied these two, and we got this column vector. All right. Now notice the W value is not 1. So it is which is 1.25. We need to divide each of these 4 values with W. So if we divide each of these 4 values with W, which is 1.25, we'll get our final answer. So we have done this division here, and we will get our final answer here, which is 44, 85, minus 200, and 1. So we only need to extract this x, y, and z value, which is x prime, y prime, and z prime. So our x prime is 44, y prime is 85, and z prime is minus 200. And we don't need to care about our W value here, which is 1. We can even derive our simple purpose perspective projection matrix from our general one, right? So for general one, we need to know the Qx, Qy, Qz, and Zp values. So in the first case of our simple purpose, which was a COP at origin, so our COP is indicated by this A point, which is at origin, and the intersection point between the projection plane and the z-axis was 0, 0, D. And if we know from our general version, this point was 0, 0, ZP. So if we equate these 2 points, we can already know. So 0, 0, ZP equals to 0, 0, D, which means ZP equals to D. And all we need to know is the vector, which is COP minus 0, 0, ZP. So we already know this COP is at origin. So COP is 0, 0, 0. We can just negate the 0, 0, ZP from our COP and get 0, 0, minus D, which is our Q vector, which means Qx is 0, Qy is 0, and Qz is minus D. Now we just substitute these values into our matrix here, matrix formula here, and we will get this matrix, which is very similar, which is exactly the one we saw in our early lecture, which was for COP at origin case. The same thing can be done when our projection plane goes through the origin. So in this setup, our COP is here, which has a coordinate of 0, 0, D. Again, D is the distance between the projection plane and the COP. Our projection plane is here, and the z-axis passes through this projection plane, intersecting at the point indicated by P, which is actually the origin, because every z value on this projection plane has a z value of 0. All right, so our COP is 0, 0, D, and we can, if we equate this 0, 0, 0 point with our 0, 0, ZP, we can say ZP is 0. All right, now we already know ZP, we can calculate our Q vector. So our Q vector formula is COP minus 0, 0, ZP, which becomes 0, 0, D, which means Qx is 0, Qy is 0, and Qd is 0. We got to know the 4 values needed for forming our matrix. So if we put these 4 values into our matrix formula for general purpose, we'll get this matrix, which matches exactly with our matrix for projection plane at origin from our previous lecture. So you can see with our general purpose projection matrix, we can service everything. So the COP is not necessarily need to be on the z-axis, it can be anywhere. And with this in mind, we can perform every kind of perspective projection. Thank you everyone. Assalamu alaikum.